Please, everybody, fill out the customer satisfaction form from the Newton Institute. And also, should you write any papers arising from your work here, please also acknowledge this program and the Newton Institute as well. We'll send an email about that. Okay, that was all the announcements. And without further ado, I'm very pleased to introduce Tomasz Steifer, who will speak on learning and randomness.
Thank you. I hope I can be. I hope I'm loud for the online people as well, if there are any. So my talk will be, I think, more philosophical than mathematical, which is good because it will be a little bit relaxing, and I think that perhaps most of people are quite tired. So, but I will try to sketch the proofs because they're easy, but they will be easy, so I don't think it will be very tiring. So, okay. So consider this. We know that there are delta 02 Martin-Love random reals. And we know also by the limit lemma that delta 02 are approximable in a computable way. So that's we have a function that for each index, well, it will guess an answer, and after a finite time, it will fix on the correct answer. For this reason, also sometimes these sequences are called, the sets are called learnable. So if we want to have a nice philosophical notion of randomness, then perhaps this is something that we don't like, we wouldn't like, that we have a random outcome that is still in some way approximable or learnable. And we also know that this phenomena happens only at Martin-Love randomness. If we go higher, then the delta 02 disappears. So this is one of motivation. And there was this paper in 2008 by Osherson and Weinstein. These are the guys who work on randomness, but more from the psychological perspective. So what people recognize as random strings and so on. And they had this paper where, in Review of Symbolic Logic, where they make an argument based on that perhaps Martin-Love randoms are too weak as a nice notion of randomness. I'm not gonna argue if that's the case, but that's the motivation they had. And this, well, this inspires we'll try to characterize classes of randomness by in a framework of formal learning theory. So I think that most of people here are more or less know what's formal learning theory and how does it work. Usually, I think we ask about recognizing particular sequences, but here I will be interested in recognizing classes. So I'll have I'll consider learners, which are just computable functions that look at the prefix, a finite number of information about the set, and gives an answer, which is a guess whether the set belongs to some class or not, whether it has some property or not. And the general idea is that, well, we will define a notion of randomness. Well, so suppose we have these learners that are devised to recognize some rare properties. By rare, of course, I mean measure 0. And we would like intuitively we would like that, well, a random sequence is not recognized to have some rare property. Okay, so the thing is, what does it mean to recognize? And well, we'll define different notions of success, and this will correspond to different classes of randomness. So already in their paper in 2008, Osherson and Weinstein observed that one can give learning theoretic characterizations of about weak 1 randomness and weak 2 randomness. So let me remind you the definition that a set is called weakly n-random if it doesn't belong to any pi01 set of measure 0. And okay, so I will be the results are which I will be presenting, they hold for arbitrary computable probability measure. If someone prefers, you can think that what is happening is just on the uniform measure. So the most natural notion of success seems to be as follows. Well, the learner reads prefixes of a sequence. And well, recognition means that after finite time, the learner fixes his answer on a positive answer, yes. And well, okay, so we consider all the learners such that this happens with probability 0. That with probability 0, with probability 1, the learner never fixes his answers on 1. So as we have here, the measure of sequences such that learner answers 0 only finitely many times, this is a measure 0 event. And we can get a definition of weak 1 randomness by saying that, okay, set is a weakly random if and only if there is no such computable learner, F, who would have this property, but who would fix his answers on the sequence. And well, it's very easy to see that this is actually true, because well, in one direction, well, cofinality can be expressed as pi01 sets, and by the assumption we make on this function, these sets are measure 0. And well, in other direction, it's also very easy, because well, if we have an X which is not weakly random, then we have a pi01 set of measure 0 that's witness that fact, and we just enumerate its complement, and as soon as we find that X is in the complement, we start answering 1, and this gives us the learner. Okay, so to get weak 2 randomness, we need to weaken our notion of success a little bit. So now, instead of converging out the positive answer, the success is that the learner answers yes infinitely many times. So this is something that will happen with probability 0. And we say that a set is weakly 2 random if there is no such learner that would answer yes infinitely many times on the sequence, while this is something that should happen with probability 0. And again, the proof is not very demanding if someone is accustomed to these notions, to pi01 class, to computability. So, okay, so in one direction, okay, so if you want to avoid computable limits by some rational delta, then this is a pi02 property or something like that. For n, there exists k and so on, such that this is, well, actually we don't have to look at avoiding, we just put 1 here because we have 2 values. So this is pi02 property, and this already gives us one implication. The other implication is not hard that much as well, because, well, we only had to notice that instead of considering pi02 sets, we can consider this generalized Martin-Lev test. So we have a uniformly sigma 0, 1 sequence of sets, such that their measure converge to 0. And we can also assume that they have this property that the next set is contained in the previous one. So we just enumerate elements of these sets, and once we find the longer prefix in the next set, we give the answer 1. So if we are in an intersection of these sets, then we'll be answering 1 infinitely many often times, but this happens with probability 0. Okay, so more recently, Zapora Blando, I think like 2 or 3 years ago, she provided a similar characterization for Martin-Lev randomness and Schnorr randomness. And this characterization, I suppose it doesn't look very surprising. This is basically what we would expect. So this is like the definition, like the characterization for weak to randomness, but this measure theoretic condition here is, well, approximated by a set of conditions such that we have computable bounds on their measures. And so we can bound the number of positive answers is bounded by 2 to the minus of n. And to get Schnorr randomness, well, as we can expect, instead of having bound here, these measures are actually uniformly computable numbers, similarly as in the definition of the Schnorr test. Okay, so, and this is actually also, well, to prove this is a little bit more involved, like to write the proof, but the general idea, at least for Martin-Lev randomness, is quite easy. So for one direction, well, one direction is immediate because this gives already a Martin-Lev test. And if we are not in this test, namely if that happens, then we are not Martin-Lev random. But for other direction, well, she in her paper does it by integral test. But I was thinking about this, and I think that like simpler argument is just to consider. Okay, so this I have already said. I think the simpler argument is just to consider martingales, and we know that well, so to just recall, the martingale is this function that takes prefixes and outputs rational real numbers, and we have this fairness condition just like in a probabilistic martingale. And martingale succeeds fairness condition, which says that the expected value after the bet is equal to the value before the bet. And the martingale succeeds if it earns unbounded, if it's not bounded on the sequence. And we know this is a basic theorem known to everybody here probably, that a sequence, the Martin-Lev randomness can be characterized by lower semi-computable martingales, or left C, if someone prefers that name. So no lower semi-computable martingale D which succeeds on E without the switch. Sorry. No, yes, with the switch. Okay, so so how we can get this function? Well, we can look how much the capital increases, and once it increases certain bound, we answer 1. Then we have a bigger bound, and we wait until we see that bound, and only then we put 1. And since we have a very nice bound on the probability of that happening by something that in Downey-Hirschfeld's book is called Komogorov inequality, but basically it's just Markov plus the fairness condition. So we will fix an appropriate sequence very fastly increasing, and we have n ones only if we have seen. So our function will be that it answers 1 n times only if the martingale exceeds the capital. So we have this Komogorov inequality. So I suppose that to get exactly the same bound as we have here, we'll have to consider 2 to the n. So if we exceed the capital by 2, we answer 1, and then only the second one once we exceed the capital by 4, by 8, and so on. And by this bound, we get a bound on the number of positive answers for the function. Okay, so this is one way to prove it. And so Zafora Blanda also asked what notions of randomness may be characterized in, well, so we can consider maybe perhaps different notions of success for the learners. And one idea would be to look at the density of positive answers. So for instance, we don't fix on answering 1 after finite time, but we are still allowed to say no, but the density of answers approach to 0 or something like that. So in particular, she asked about this class. And well, I have submitted the abstract of this talk 2 years ago. And for 2 years, I was convinced that I have an answer to that problem. But when I was preparing slides, it turned out that I was wrong. So it is still a problem, I think. So I was trying to, during this last week, I was trying to find a proof for that, but I wasn't successful. So maybe it's not that easy. Maybe it doesn't respond to any known notions of randomness. So basically, okay, so the notion is as follows. We ask that, well, the notion of recognizing is just approaching the density of answer approach to 1. And well, this is supposed to happen with measure 1. And we ask that there is no such that for a sequence X to be in the class LD, there is no such computable learner who has density 1 of positive answers, but this is something that should happen with probability 0. Okay, so I have one observation about this. So if set is not weakly to random, then it's definitely not in this class. And this is actually quite easy to see. Well, I'll try to, well, this is, if I draw the picture, then I think everybody will immediately see that it's true. So suppose we have this learner F, and well, this is the number of his answers, and it's increasing. And we want to have something like that, that our density perhaps will be going like that. So we just have to map this to this. And well, we know how to do that. So one idea is once we saw k positive answers for the F, so we have F which is in the sense of, sorry, maybe I wasn't so clear. So we have F which is in the sense of this definition, that it answers 1 only, that it's supposed to answer 1 only finitely many times. So we look at, and we want to construct G, which will be the one with the density property. So we look at what F does, and once we saw k positive answers, we ask G to output k ones and 1 0, which gives us the density k over k plus 1. And since if k is this number k is increasing, then our density is increasing and we go to 1. But if we have only finitely many positive answers, then at certain point we fix on that, and our limiting density is not 1. So this is also an easy observation. And I don't know actually, well, I don't know if that's a good bound. Well, because, well, okay, so this is a complicated property. It's not pi 0, 2. So it's probably not weak to randomness. Maybe somebody here had some idea how to deal with this. Pi 0, 3, but it doesn't seem that these are pi 0, 3 random, or maybe like weakly 3 random. Would you conjecture that? Okay, well, we can talk about that later. Okay, so I will give some other observations about how can we characterize weak to randomness and weak one randomness using density. So and these have also very easy proofs. So we can have this for weakly to randomness. We have that, well, we expect the density of answers to go 0 almost surely, but on the guy, it happens that we are sometimes thinking that we should say yes for a long time, that our density goes. So being weakly to random, sorry for that mu, weakly to random means that just for no function with that property, this happens. And well, for one direction, if this happens, we just fix some delta, and every time the density goes over higher than delta, we answer yes. And this gives us, well, this is this direction, and the other direction seems to be pretty obvious too. Okay, and we can also characterize weak one randomness using two separate limits. So a sequence will be weakly one random if there is no computable function such that, well, with probability 1, the limit is 0, but we obtain on the sequence the limit 1 of positive answers. And again, the proofs are quite easy. So, well, in one direction, if we have just two possibilities of going either here, if we are interested in two possibilities, either going here or going here in the limits, so we just fix a number between 0 and 1. And while we are below, these densities are below this number, we answer 0, and if they go up, we answer 1. So if that happens, at a certain point, we will fix on answering 1. But if that happens, we will be answering 0 all the time, and that's it. And for the other direction, well, so we have a function f which answers 0. So we have an x which is not weakly random. We take a function which answers 0 only finitely many times on x. And almost surely this shouldn't happen. We should answer 0 infinitely many times. So let's k be the number of 0 answers on x. So we construct a function g as follows. As long as as f answer less than k times no, the function g will always answer yes. And once we see the k plus 1 negative answer, we just start answering no, and that's it. So here this is wrong. It should be that after some time it's, oh no, it does answer yes. Okay, sure, sorry. Okay, so we actually can make a more general observation from that. So we know by result of Jokusz and Shoup that a real is delta 02, if and only if it's a density of computable sequence. So actually we can, in this definition, we can put, instead of 0 and 1, we can put two delta 0 reals, A and B, and sorry. So here it should be A, and here it should be B. Sorry for that. So we actually can put arbitrary delta 0 reals there to get the equivalent definition. And I suppose we could perhaps do something similar here. No, something similar here with avoiding that limit. Like put here a delta 0 real number, and here we ask about avoiding this just. Okay, and so that's basically, I think, all that is known about this, that is shown about these learning characterizations. And now I would like to say a few words why I found it interesting. So I mean, it's nice that we can think about randomness using these learning theoretic notions, and it gives a nice ways of thinking of them. But I'm not sure if this is just like so very close to real world learning. But what's more interesting for me is this problem. Who was listening to my talk at Leeds has probably seen this slide already. So there is this effectivization program that I understand dates back to Komogorov, but perhaps the idea was popularized more by Vyugin. So let's say we have this probabilistic theorem, which have this form, well, something happens for almost all x. And we want to see if we can have a stronger version that's phi of x happens for all x that are random, where random is some notion of randomness that we like, or that just happen to be good for that theorem. So we know many examples. We know Borel-Cantelli lemma, which is basically Solovay tests. We have Martingale convergence, Levy law of large numbers. We know that ergodic theorems hold for randoms for different randoms with different with up to different details, let's say, or different strength. So a special case that I was interested in, like when I was learning randomness and working on my PhD, was this, that we have a uniformly computable sequence of functions which, well, suppose acting on prefixes, but they could be just acting on, well, no, acting on sequences, but suppose that they're acting on prefixes and output some real values. So as an example, well, there was a talk. So for instance, in information theory, we consider a function that approximate entropy rate. So we know that there are functions which will be taking prefixes of n, and the limit of these functions will be exactly the effective dimension for appropriate measure, and this will happen with almost surely. So this is very like an example of what could we be interested in. And okay, sorry. So the question is, if we have such a function, and we know that something like that happens with probability 1, then we might be interested, as I said, I would be interested to see if this happens also for all randoms. And from the first slide, we already know that this is not only always the case. We will have such functions that converge to some computable f almost surely, but they will fail to do that. They will behave in a weird way on some randoms. So I found it nice to, so this learning theoretic approach seems to me as a nice way of thinking when that might happen. Because so suppose we have this function that does converge on all randoms. How can we destroy it to make a function that works almost surely still, but fails on some random? Well, we take this approximation of a delta 02, and we make a learner of it, such a learner that, in the sense of this weak to random characterization, a learner which will answer one infinitely many often on this delta 02. So we'll be able to destroy the limit of the functions, but still this will happen with probability 0. So I have two, I don't know, these observations are perhaps folklore, but still it seemed interesting to me that if we take this learning, for me it was quite, it really allowed me to order this stuff in my head. So we know this is folklore, and I have already, I think, argued a proof why this happens. So we know that that avoiding a computable limit by some delta is pi02. So in particular, if x is weakly random, then if function converges almost sure, if the sequence converges almost surely, then it will converge also on the weakly to randoms. And actually, this learning theoretic characterization of Oscherson and Weinstein, this very nice, easy proof, tells us that this property already characterizes this all weakly to randoms. So a sequence is weakly to random if and only if all functions converging to computable limit almost surely converge on that sequence. And from the characterization that we had for Martin-Lev randomness, we also can have this convergence, the characterization of Martin-Lev randomness via convergences of uniformly computable sequences. And I think so this is actually interesting for me. So usually if we have such functions, how could we argue that they converge on all Martin-Lev randoms? So usually I think two situations, I know examples which goes into one of two groups. So one is that the convergence is already effective. So if we look at something like probability that fn minus f is bigger than delta, then as we can bound this by some computable function that goes to, for fixed delta, it will goes fast to 0 with n. So this is one idea. Another thing that can happen, and this is, for instance, how we prove that Doops martingale convergence is actually effective, is that we have effective bounds on the number of upcrossings. So the number of upcrossings is that we fix A and B, and such that A is smaller and B, and upcrossing is something like that we cross it here and cross it here. And for some processes, we have this nice upcrossing bounds, which says that the probability of this happening over all sequence, not up like here up to n first bits, but on the whole sequence, that more than n times is bounded by something. But this seems to be something yet different, because here we answer about how probable is that we are for n different moments below the limit. And well, if we have effective convergence, then this, I think, follows, but I'm not sure if from this follows effective convergence. And I would be actually interested in seeing natural examples when we can have such bounds, but not this or this. Sorry? No, I'm saying that we can have, like, this happens for every delta.
You think that Fn is equal to F on the set of measure 1 minus 2 minus F.
Yes, okay, right. Sure. It seems weird, right?
It is true for all delta.
Yes, yes, I agree. Okay, I agree, right. Okay, so, and I think that's it, what I've prepared. So I think, well, but perhaps when I say that these two frameworks are connected, it's more happening in my head. I don't know if I'm convincing you that this the first one is really useful to attacking this problem. But what I hope that perhaps if we try to look at problems like this one and get more and more characterizations, then perhaps by studying this very simple 0-1 framework, then perhaps we'll get answers that can help us in specific cases of probabilistic theorems here interfere whether we have this or not. I don't have any answers where this really helps us, but perhaps it could be useful. Okay, if you have any questions, I will be happy to try to answer them.
Thank you, Thomas. Questions?
Like this in analysis.
Hold on, Andre, let me bring you the microphone so the online people can hear.
There are theorems like this in analysis. I mean, effective analysis, like the back differentiation, non-decreasing functions differentiable almost everywhere, and
Yes,
and
yes,
and use computable randomness.
yes.
So, but of course, connecting to learning theory, I haven't.
Yes, yes, I would be seeing this as an examples of this general program.
Great. More questions?
I don't see any.
Oh, sorry. Valentino.
Can you go back to the slide where you used the martingale's approach to prove?
Yeah.
Okay, and that was for Martelov randomness.
Yes.
Okay, so I mean, do you think that, I mean, it seems to me that still, like, you know, this giving 0 and 1, it's, I mean, as a framework, seems kind of similar of the game that we are playing when we define randomness notion with martingales. So maybe do you expect that this, maybe looking at the connections between these two frameworks could give us more characterization? I mean, even for, like, because here we are working a lot on weekly 1 random, weekly 2 random, and so on. But with, I mean, randomness notions which are more, you know, we are usually considered defined using martingales.
Yes, well, I was actually thinking about that, if we can, well, because these arguments work for lower semi-computable functions, because, well, once we cross, we know that we are higher. But of course, if we consider computable randomness, we still have the same functions, but I don't know, well, I couldn't say what does it say exactly about the learning functions that we get. But I think it's a reasonable question. I think there are, well, I'm not sure, but I think that could be looked into. I was wondering about that too.
Anything else? Okay, thanks again.
Thank you.
All right, the next talk is at past, so we have a little break now. For the people that just joined us online, let me remind you that Stefan's talk, the next talk, is the last talk. There'll be a quick announcement about CCR 2023, and then that's it. There's no closing session like on the schedule. That's it. That's at that's 2:30, 2:30, yeah. 2:30, yes. Yep, in a little more than 15 minutes. Okay, great. So see you soon.